Welcome to our session. My name is Yong Liu. Together with my colleague Andrew Brooks, we are very excited to share our experience on developing continuous delivery of deep transformer-based NLP models using MLflow and AWS Sagemaker for enterprise AI scenarios. So here is our presentation outline with 4 sections. Let's get started with the first section with some introduction and background. So you may or may not have heard of Outreach, the company we work for. Outreach is the #1 sales engagement platform, powering more than 4,000 customers and growing. These customers include many well-known startups and multinational companies. So what is a sales engagement platform? A sales engagement platform encodes and automates sales activities such as emails, phone calls, and meetings, etc., into workflows. For example, this diagram on the left shows a workflow where you can send an email and place a phone call on day 1, and then schedule a LinkedIn message on day 3, and then send another email and make another phone call on day 5. Due to such automation, sales reps' performance and efficiencies can be dramatically improved, up to 10 times better, by doing more effective one-on-one personalized outreach. In addition to automation, we are also adding intelligence into the sales engagement platform. That's where machine learning, NLP, and AI come to play. So how does machine learning NLP help? By using our product, sales reps generate a lot of data, such as emails, call scripts, and engagement logs, etc. We then leverage machine learning NLP to perform continuous learning from this data and combine with knowledge to provide prediction, recommendation, and guidance for the continuous success of reps. This becomes a flywheel shown on the left. The reason for continuous learning is that sales process changes due to various reasons. We already observed that COVID-19 changes how sales reps using content, and that's why it is important to enable continuous learning and guidance. One particular use case we will highlight in this talk will be guided engagement, which we will discuss later. However, before we really enjoy the benefits of machine learning, NLP, and AI, we have some barriers to overcome. Now I'll hand off to Andrew to continue the discussion.
So now, to set the stage and motivate what we've implemented and why, we'll discuss some of the implementation challenges we've faced here at Outreach. While we'll ground this discussion within the context of our experience, we expect many of these challenges to be shared across other enterprise machine learning teams. So first, challenge 1, the dev-prod divide. If you've ever felt like a model developer throwing a model over the wall to an ops team and that's the last you've seen of it, or an ops team catching a black box model with unclear requirements and interfaces, this cartoon might speak to you. When model developers are isolated, when they can't see or use code from the prod environment, they can't test on live data, the data streams that actually feed the model in the product or the application. And why is this a problem? So this often leads to misspecified model pipelines, which produce bad predictions, which in turn produce complaints from users or even paying customers. And that pain is compounded even more when model developers can't reproduce those reported bugs or issues. Remediation could involve manually diffing a dev and a prod pipeline to understand root cause. We've been there. It's costly, it's inefficient, it's not fun, and it's not necessary. Lastly, it's also wasteful when production-grade machine learning tooling that's developed in prod cannot be used for future model development. This is the scenario where a V1 model has been trained, productionized, and shipped, but V2 model training is restricted to the early iterations of notebook and ad hoc code used to develop V1 model. Challenge 2, dev-prod differences. These are the scenarios where differences between dev and prod pipelines are inevitable, or sometimes desirable, the good differences. One common difference is that the data sources for model training and model scoring in production are often different. Data used for training is typically from a persistent data store, analytics data used internally within an organization to build models and reports, without the danger of directly modifying customer-facing data or putting load on production applications. Prod data for scoring is often streamed, not static, the data that is customer-facing, and might have been off limits to model developers during training. Often these data sources require different preprocessing pipelines. Second difference is the inclusion of product-specific or business logic that is desired for prod, model scoring, but not during training. For example, the scoring pipeline in prod might want to suppress predictions where the model is not confident, but no such filters are desirable or even existent for the training pipeline. So challenge 3, arbitrary uniqueness. Without a framework codifying common design patterns, components have a tendency to be individually great and powerful, but collectively suboptimal and even counterproductive when connected to other components in a pipeline or system. This is a scenario where the whole is not greater than the sum of its parts, despite the individual uniqueness and greatness of those parts. This is probably occurring when deploying each new model feels like a special case and reinventing the wheel for patterns that, for components that mostly kind of exist already. Not only does this involve a lot of extra development, but it often produces pipelines that are not self-documenting. For example, if gates and deploy mechanisms of a pipeline are not consistently defined, it's unclear how to even run the pipeline. Ability for reuse across projects and models and integration within a bigger system is limited. Naturally, pipeline maintenance and extension is painful and inefficient, even more so when onboarding new engineers or developers. So last challenge, challenge 4, provenance, specifically provenance from models to source code and source data. Why do we need this? If we don't know what's running in prod, we can't reproduce issues and bugs reported by users, as we discussed in challenge 1. A second negative effect is that model pipeline changes might make teams grimace with fear rather than excitement for shipping improvements. This is often the case when we're not confident that a mechanism exists to consistently determine exactly what's running in prod, how it got there, how to reproduce it, or promote a new model to replace it. Lack of provenance can also compromise historical and temporal analyses that use model predictions. If released models aren't versioned, this could compromise benchmarking or historical analyses that disguise real-world behavior changes that are actually caused by just undocumented model changes. So given these pain points and challenges, we'll discuss how we overcome some of them in the context of a real use case at Outreach. Afterwards, we'll also share some of the challenges we continue to face and thoughts for addressing those in future work. So the use case we'll walk through is the Outreach Guided Engagement feature. It's an inbox-based intelligent experience powered by an intent classification model under the hood. When sales reps receive replies from their prospects, existing or future customers, Outreach predicts and displays the intent of that prospect's email. Perhaps positive, the prospect is willing to meet, or in this case, objection, the prospect already has a solution. Based on the predicted intent, relevant content is recommended to the sales rep. For simplicity, our talk will focus on just the intent prediction component, text classification, not the content recommendation component. While we discuss our use case and pain points, we'll reference where we are in the machine learning full model lifecycle. In this talk, we'll focus on the middle 4 stages, starting with model dev. This is where we run many experiments offline to quickly iterate and develop the model logic of the winning model that we want to ship. In pre-prod, we mature and package that winning model logic into software that gets published for use in production. For our use case, this publishes a Docker image and trained model artifacts. The last 2 stages we'll talk about model staging and model prod, is where the model is hosted, exposing an endpoint for outreach, our product application, to call. So starting with the model dev phase for our use case, this is where most of our development was in Databricks or Jupyter notebooks and code repositories used only for offline developing model logic and running offline experiments. Even though we didn't intend to ship this code, we did leverage MLFlowtracking to tie experiments to results. This provenance prevented unnecessarily repeating the experiments multiple times and provided context and baselines for the winning model. Our model development often includes many modeling frameworks and techniques, each with different APIs. For this particular model, we explored SVMs using scikit-learn, fasttext, Flare. Ultimately, we chose the Hugging Face Transformers library for its unified API to state-of-the-art deep transformer architectures and pre-trained language models. State-of-the-art is a quickly moving target in this domain, so a project with an active community quickly closing the gap between published research and implementation was important to us. While strong in momentum, the Hugging Face Transformers library is a relatively young project and not yet a native MLflow flavor. We avoided arbitrary uniqueness by extending MLflow and writing our own MLflow flavor that lets us plug into the rest of the MLflow framework. So what does that mean? That means we wrote a tiny wrapper class, shown on the left side, that maps the Hugging Face Transformers library, which itself wraps a multitude of powerful architectures and models, to the standard MLflow models API. And so what does this get us? Among other things, this buys us a standard mechanism for model serialization, both saving and loading. We also wrote a transformer classifier class that's scikit-learn pipeline compatible, so that we can chain our transformer model with pre and post processing steps. And why do we need that? So we need this when we have scenarios like in challenge 3 where train and prod pipelines need to be different because the data sources are different, or there's different business logic desired to be in production but not training. One example in our scenario is filtering email auto replies from production scoring but not during model training. And here we have just an example of a saved transformer model from the MlFlowtracking server API, just the MlFlowtracking server, and its associated artifacts shown on the left. The code snippet on the right shows just a couple lines to log or load the model. This bypasses the arbitrary uniqueness involved with manually dealing with Python's pickle or other serialization protocols, which can be finicky and pass the burdens to the consumers of the model. In pre-prod, where we're intentionally rewriting code and refactoring it from the dev notebooks into software that will actually run in production, we adopted MLflow's MLProject pattern. MLProject is a fairly lightweight layer that centralizes entry points and standardizes their configurations and environment definition and management. Again, a cheap way to avoid the pain associated with arbitrary uniqueness by providing a self-documenting framework for the pipeline. From a workflow perspective, we found the flexibility for MLProject to run remote code and execute on remote clusters actually also accelerated our development and tightened up some of our testing and code reviews, such as reproducing model results. By referencing the code to run by GitHub release tags or commit SHAs, shown in red, we're able to buy ourselves improved provenance, tying the source code directly to the model artifacts and results in MlFlowtracking. From a workflow perspective, this also prevents the hassle of manually cloning and running local code. Referencing the remote execution environments, shown in green, allowed us to develop code outside of Databricks notebooks in our IDEs of choice, while also leveraging the power of the Databricks runtime for execution and powerful GPU-based clusters.
Now, suppose we have a production-grade trained NLP models for intent classification of emails. Does that mean we can now deploy to production? Not so soon, actually. That's because there are unavoidable differences in terms of logic in the deployment environment, which we have been discussing in our challenge part. That's why we create 3 progressively evolved models for final deployment in a host environment. In our case, that's the SageMaker. First, we create a fine-tuned trained transformer classifier, and then we wrapped the same classifier with pre-process and post-process steps, which we call pre-score and post-score filters. And this entire wrapped pipeline becomes a scikit-learn pipeline. This is basically the pipeline shown on the middle, in the middle of the diagram. The reason we want to have some pre-score filter is because we want to add additional logic, such as whether to parse the email to get the current reply message body only, or the full email thread. Or if the email size is too big, we may decide to not score it at all. Or maybe we want to use some caching mechanism when the email content is exactly the same. We can just return the caching results of the prediction. So for the post-processing part, post-score filters, we could also add additional model metadata in the response so that we can track provenance from the caller side. Note that there is no model logic change in the classifier itself, but having this second model pipeline is much flexible. Lastly, in the production environment, we don't want the model to access our private GitHub because accessing a private GitHub requires either a GitHub token or SSH key, which are security concerns in an enterprise production environment. So we create a third model which packages all private Python dependencies into private wheels and then burn them into the Docker image so that at the deployment time, the model can reference them without accessing the private GitHub. So now we are ready to fully automate the deployment through CI/CD tool. For CI part, which is the continuous delivery part, a continuous integration part, we use CircleCI. The CircleCI pipeline not only does unit testing and style enforcement, but also runs the entire train, test, wrap, and deploy all the way to a SageMaker endpoint at staging, using a subset of the training data. This safeguards any code checking. Note that several steps of CircleCI are reusing the same MLProject entry points we discussed earlier. This also allows us to even break the dev-prod divide because we could also use the same CI pipeline to run some experimental code or model changes without reinventing wheels. Now for CD part, that's continuous delivery and rollback. We use Conquers at Outreach. This pipeline has two well-defined human gates. First, to trigger a full model building, a designated person needs to kick off the entire pipeline. And once it passes a regression test and make sure that we are not getting a worse model than previous one, then a second human gate will also need a person to promote the model to a production endpoint. Here, the last step, we show that we can deploy to AWS SageMaker US East and the US West region. So in the CI/CD automation, we not only log the model, but also register the model using MLflow model registry. From model registry, we can clearly see which version of the model is in production and which is in staging. And if you are curious about more details of the model, you can just click the version link and you can find out the provenance information of the model. So now we have done the full lifecycle implementation. How well did we address the 4 challenges we talked about at the beginning? we feel like we did pretty well on all 4 stages in terms of provenance checking. Except for the model dev stage, we also did well in overcoming other 3 challenges. In particular, we feel like we did very well in embracing the dev-prod divide and arbitrary uniqueness during model pre-prod when we wrote the production code and published transformer flavor model, making model code and the deployment process reusable and repeatable. However, one area we are not fully satisfied is during model staging, we did not really test with production real-time streaming traffic, which could have been done through some A/B testing mechanisms before we promoted the model to production. That's something we will address in the future. So in conclusion, we highlight 4 typical enterprise AI implementation challenges and how we solve them with MLflow, Sagemaker, and CI/CD tools. Our intent classification model for guided engagement has been deployed in production and in operation using this framework. Our next steps, in addition to what we mentioned, testing in staging for the model using A/B testing kind of mechanism, we are also addressing the following things. First, incorporating model in production feedback loop into annotation and model development cycle. Second, we are further improving the annotation pipeline to have seamless human-in-the-loop active learning and model validation. Finally, we would like to thank everyone in the data science group at Outreach who have contributed and supported this project. If you are interested in knowing more details about our experience and about Outreach platform, please contact us at this email addresses shown in the screen. Thank you very much.